Hello, so let's continue the book of Joyce Farell, Programming Logic and Design. So we've discussed previously chapters 1.1 to 1.3, and now we're going to continue with 1.4, using pseudocode statements and flowchart symbols. So when programmers plan the logic for a solution to a programming problem, they often use one of two tools, pseudocode, pronounced pseudocode, or flowcharts. So pseudocode is an English-like representation of the logical steps it takes to solve a problem. Pseudocode is a prefix that means false, and to code a program means to put it in programming language. Therefore, pseudocode means false code or sentences that are similar to those written in a computer programming language but do not necessarily follow all the syntax rules of any specific language. So basically, pseudocodes are can be a blueprint for a lot of programming languages, especially because it is written primarily because of the logic structure of the program that you want to build. It's basically a guide that a lot of programming languages can refer to. So it doesn't follow the syntax of any specific language, but it's very similar to English, okay? So it follows the English language, not English programming language, but English structure, like how we normally read and write in English to understand the program flow better. Next is a flowchart. So unlike a pseudocode, a flowchart is a pictorial representation of the same logical steps. So if pseudocodes are lines of understandable steps to be like an kind of a blueprint for a program, a flowchart is also kind of a blueprint, but it is more of a pictorial representation of the steps. We use different symbols and shapes to create a flowchart. We also use lines and we can represent different structures. We have three structures to be discussed. We have sequence, we have the second one is the selection, and third one are the iterators or the looping. Okay, next, writing pseudocode. So you already have seen examples of statements that represent pseudocode earlier in this chapter. There is nothing mysterious about them. The following five statements constitute a pseudocode representation of a number doubling problem. So pseudocode always has indentations. Start at an indent so that we could see it clearly, okay? Because, for example, when we code, we want to know the exact blocks of the code so that we would be syntax error free. For example, in Python, we use indentation is very important, rather. So if we don't indent it properly, we might have a syntax. I mean, not necessarily syntax, but we're gonna have an error in our output. So start, input my number. My answer is equals to my number times 2, output my answer. Okay? So we inputted the a data. Stored in a variable my number. Then we create another variable that doubles that input my number. Then the output is my answer. So if my number is, for example, 2, then my number will multiplied by 2 and will be stored to the variable my answer. And the output asks for the my answer, which has the value of 4 since we multiplied it by 2. Okay. Okay, it's the same thing. So using pseudocode involves writing down all the steps you will use in a program. Programmers preface their pseudocode with a beginning statements like start and end it with a terminating statement like stop. The statements between start and stop look like English and are indented slightly so that start and stop stand out. Most programmers do not bother with punctuation, such as period and at the end of pseudocode statements, although it would not be wrong to use them if you prefer that style. Similarly, there is no need to capitalize the first word in a statement, although you might choose to do so. Pseudocode is fairly flexible because it is a planning tool and not the final product. Therefore, for example, you might prefer any of the following. So instead of start and stop, you could use begin and end. Instead of writing input my number, you could use get my number or read my number. Instead of writing my answer is equals to my number times 2, you could say my number times literal wording times, and my answer is assigned my number doubled. I would not recommend this one since it is filled with words. It is almost like a sentence. It is actually a sentence, but would you rather read this or this one that has a bit of a mathematical that uses a mathematical operation equal sign and integer 2. That's easier to read. Okay. So this one is the ideal because it just balances the English language and mathematical operations. So next, instead of writing output my answer, many pseudocode developers write display my answer, print my answer, or write my answer. So the point is that pseudocode statements are instructions to retrieve an original number from an output device and store it in memory where it can be used in a calculation and then get the calculated answer from memory and then send it to an output device so a person can see it. When you eventually convert your pseudocode to a specific programming language, you do not have such flexibility because specific syntax will be required. For example, if you use C# programming language, you write a statement to output the answer to the monitor, you can code the following. Console.write my answer. The exact use of words, capitalizations, and punctuations are important in the C# statement, but not in the pseudocode statement. Pseudocode standards might be slightly different in an organization where you work. Following is a list of the standards used in this course. So start and stop. We already scan through that. So program statements are indented with spaces. Says each program statement appears on a single line as possible. When this is not possible, continuation lines are indented. Program statements begin with lowercase. No punctuation is used to end a statement. Each program statement performs one action. For example, input processing output. Shortly, you will learn about programming modules. Two additional standards will apply to modules. Whenever a module name is used, it is followed by a set of parentheses. Modules begin with a module name and end with a return. So these are always aligned. So as you learn to create pseudocode and flowchart statements, you will develop a sense of how much detail to include. The statements represent the main steps that must be accomplished without including minute points. The concept is similar to writing an essay outline in which each statement of the outline represents a paragraph. Drawing flowcharts. Some professional programmers prefer writing pseudocodes to drawing flowcharts because using pseudocode is more similar to writing the final statements in the programming language. Others prefer drawing flowcharts to represent the logical flow because flowcharts allow programmer to visualize more easily how two program statements will connect. Especially for beginning programmers, flowchart is an excellent tool that helps them to visualize how the statements in the program are interrelated. You can draw a flowchart by hand or use software such as Microsoft Word or and Microsoft PowerPoint that contains flowcharting tools. You can use several other software programs such as Lucidchart, Logarithm, so on, to create flowcharts. When you create a flowchart, you draw geometric shapes that contain individual statements that are connected with arrows. In a flowchart, you use parallelogram to represent input symbol, which indicates an input operation. You write input statement in English inside of parallelogram. The input symbol used in flowchart is a parallelogram. Parallelogram is indicated with the following step inside it. Input my number. Okay, that's very easy. Again, input and output are indicated inside a parallelogram. Okay, there's no any process statements in a parallelogram. For example, pi number times 2, or my answer is equals my number times 2, as earlier we've discussed that, right? So, can we put that in a parallelogram? No, because those are process statements. You can only put it, you can only put input statements inside a parallelogram because the parallelogram is the input symbol. Next, arithmetic operations or the process statements that we discussed earlier are examples of processing. In a flowchart, you can use rectangle as a processing symbol that contains processing statement shown in this figure. So as we said earlier, we could use my answer equals my number times 2 inside a rectangle because we store processing statements inside a rectangle. The processing symbol used in the flowchart for processing statements is a rectangle. A rectangle is indicated with the following step inside it. My answer equals my number asterisk 2. Okay. To represent an output statement, use the same symbol as input statements. The output symbol is a parallelogram, as shown in figure 1 to 5. Parallelogram is used for both input and output. It's often called input-output symbol. So we discussed that earlier. Some software programs that use flowcharts, such as Visual Logic, use a right slanting parallelogram to represent input and a left slanting parallelogram to represent output. As long as the flowchart creator and the flowchart reader are communicating, the actual shape is irrelevant. This course will follow the standard convention of using the right slanting parallelogram for both input and output. So to show the correct sequence of statements, use an arrow or flow lines. The arrows that we see in the flowcharts are called flow lines, okay? To connect these steps, whenever possible, most of the flowchart should read from top to bottom or left to right on a page. So that's why we read English. So when flowcharts follow this convention, they are easy for us to understand. So to be complete, a flowchart should include two more elements: terminal symbols or start-stop symbols at each end. Often you place a word like start or begin in the first terminal symbol and a word like end or stop in the other. The standard terminal symbol is shaped like a racetrack. Many programmers refer to this shape as a lozenge because it resembles the shape of the medication you might use to soothe a sore throat. So, okay, so we add another shape, which is a lozenge shape or like a medicine capsule shape or whatever you see this shape as in real life. But we often see it in medicine, right? So we use this lozenge, okay, then it indicates the start and stop. Usually, after lozenge, input my we input statements, then process and output. This is just this basic sequence of um an IPO. Okay, so to the code of a program that doubles number. The float. Oh, this is the details for this. This is easy as we discussed earlier. Program seldom creates both pseudocode and a flowchart for the same problem. You usually use one or the other. In a larger program, you might even prefer to write pseudocode for some parts and draw flowchart for others, meaning we could integrate both in a program, not both for the whole program, but we could pick a part of a program and use flowchart for this and pseudocode for that. For example, a part of the program demands on more logical flow or like how the interconnectedness of the variables and the methods used is in the program, then if you want to really navigate it, then we're gonna use flowchart. But if you prefer as more simple statements that could easily be translated into a programming language, you would use or most programmers would prefer pseudocode. But nevertheless, both can be used for writing program. Okay. So when you tell a friend how to get your house, you might write a series of instructions or you might draw a map. Pseudocode is similar to written step-by-step instructions. Flowchart is a map visual representation of same thing. Okay. So here are other um, shapes and visual representations of for flowchart. So again, we have the Lausanne shape for terminal. We write start and stop in the Lausanne inside the Lausanne shape. Next is a flow line. We connect the shapes with a flow line. Okay. A point that ends with an arrow, I mean an end that has a arrow symbol at the end. Then we have input and output in a parallelogram process or the arithmetic operations will be processed inside a rectangle. Decisions, we we tend to use this conscious or the diamond shape for the iterations and the selections. For example, if my answer is greater than 3, is it true or false, then it will run there. Or you could also loop while it is not equal to a certain number, continue to loop until it becomes true. So we also have internal modules call, external module call. Those are used for the methods. Okay, next is repeating instructions. So after a flowchart or pseudocode has been developed, the programmer needs only to buy a computer, buy a program language compiler, learn programming language, so on, put in production and stuff. We already discussed a program development cycle. This is not okay, this is not program development cycle. This is what you need to do after you learn, I mean, after you paid a flowchart or pseudocode. But we're gonna skip that part. Okay, so this part is repeating instructions. Okay, if we have too many instructions, that so-called repetitive instructions, we don't, in an efficient program, we don't put it every time that it's there. For example, in this, we input my number, then we multiply it by 2 and store it to my number, my answer variable. We output my answer, then then we repeat it more and more times because what? It's not efficient. And it says here the program represented in that figure does not double 1,000 10,000 numbers. Doubles only one. You'd execute the program 10,000 times, of course, but that would require you to sit in this copy and run over and over again. So inefficient to the code for a program that doubles 10,000, right? You don't manually encode everything because you want to reach 10,000. Okay? So there's a solution for it and we call it loop. So the better solution is to have a computer execute the same set of instructions repeatedly. Repetition of series of steps is called a loop. With this approach, the computer gets a number, doubles it, displays a number, and then starts with the first instruction. The same spot in the memory called my number is reused for the second number and for any subsequent numbers. The spot in memory named my answer is reused each time the stored result of the multiplication operation. However, the logic illustration in the flowchart 1.9 1.9 contains a major problem. The sequence of instructions never end. The program situation is also known as infinite loop, a repeating flow of logic that has no end. You will learn one way to handle this problem later, okay? The problem with this is that we want to loop this. Oh no. So we said that to have a more efficient program in situations where we tend to repeat the process that we use for a data or set of data is instead of repeating it manually, we use loops. However, in this flow chart, we could say that it's inefficient because it never ends. Why does it never end? For example, we start input my number, we put a number, and then we multiply it by 2 and start to my answer variable, then we output it. Then we repeat and repeat again. Where's the end, right? It doesn't point to any end because it's just looping continuously and infinitely. So a flowchart for an infinite number doubling program. The following steps are represented in flowchart. So okay, two truths and a lie. When you draw a flowchart, you use a parallelogram to represent input operation that's true. When you draw a flowchart, you use a parallelogram to represent. Okay, that is the lie. Okay, so this is true, and number three is true because when you draw a flowchart, you use a parallelogram to represent an output. So you don't use a parallelogram for a processing operation, you use a rectangle. So the correct answer is rectangle. Okay. I think that I don't know, I think we could still use this. Oh yeah, okay. Let's run another subchapter 1.5. So 1.5 using a sentinel value to end a program. Okay, this is very important, especially in loops. Okay, using a sentinel value to end a program. The logic in the flowchart for doubling numbers shown in figure 1 when it has a major flaw, the program contains an infinite loop. Okay, if, for example, the input numbers are being entered at the keyboard, the program will keep accepting numbers and outputting their doubled values forever. Of course, the user could refuse to type any more numbers, but the program cannot progress any further while it is waiting for input. Meanwhile, the program is occupying computer memory and typing up operating system resources. Refusing to enter any more numbers is not a practical solution. Another way to end the program is simply to turn off the computer. But again, that's neither the best solution nor an elegant way for the program to end. A better way to end the program is to set a predetermined value for my number that means stop the program. For example, the programmer that use that and the user could agree that the user will never need to know the double of zero, so the program could enter a zero to stop. The program then could test any incoming contained in my number, and if it is zero, I stop the program. In a flowchart, you represent testing a value or evaluating an expression by drawing a decision symbol, which is shaped like a diamond. The diamond usually contains a question or evaluation, the answer to which is one of two mutually exclusive options. All good computer questions have only two mutually exclusive answers, such as yes or no or true and false. For example, what day of the year is your birthday? It is not a good computer question because there are 366 possible answers. However, if your question is your birthday June 24, it is a good computer question because it is answerable by yes or no. So make sure that the statements you're gonna put in the decision symbols are answerable by yes or no. The question to stop the doubling num program should be, is the value of my number is entered equal to zero, or my number is equal to zero for short. Complete portrait is looks like this. So we input my number equals to zero. If it is yes, stop. This no, we continue looping. What is the error in this? So it is not structured. So kasi we have in flowcharts called structured and unstructured. It's better to follow and always follow the structured flowcharts. Programmers use different notations when they want to express a negative question into the code or flowchart. For example, if a programmer wanted to ask whether my number was not zero, the programmer might write, my number not zero. Could also use this sign, not equal. And we could also use the less than and greater than symbol together. So one drawback to using zero to stop a program, of course, is that it won't work if the user does need just need to find the double of zero. In that case, some other data entry value that zero will never need, such as 999 or -1, could be selected to signal the program should end. A pre-selected value that stops the execution of a program is called a dummy value because it does not represent real data but just signals to stop. Okay? Sometimes such value is called sentinel value because it represents an entry or exit point that a sentinel, like a sentinel who guards a fortress. Okay. Not all programs rely on user data entry from a keyboard. Many read data from input devices such as disk. Mhm. Okay. So any no, no. Mm, okay. Fortunately, programming languages can recognize the end of data in a file automatically through a code that's stored in the end of data. Many programming languages use the term EOF for end of file to refer this marker that automatically acts as a sentinel. Okay, this course uses EOF to indicate the end of data whenever a dummy value is impractical or inconvenient. Okay, we will learn in the next chapters on how to create an efficient flowchart or the structured flowchart and compare it to unstructured ones. So let's try this two truths and a lie. A program containing an infinite loop is one that never ends. That is correct. A pre-selected value that stops an execution of a program is called dummy value or sentinel value. That's correct. Many programs use the term FE for file and to refer to a marker that automatically acts as a sentinel. This is the one that is wrong. It's called EOF. So I think that is it for this video. Okay, so we run through using pseudocode statements and flowcharts, writing pseudocodes, drawing flowcharts, and repeating instructions. We use sentinel value to end a program. Okay, so next we will study the 1.6 to chapter 1.7, which is the end of chapter 1.